So here is one way that we can use valence electrons to determine some things about some chemical properties. Before I talk about this, I want to bring up a hugely important idea that really governs most of the things in chemistry, and it is this. All systems in nature tend to reach an arrangement with the lowest possible potential energy. This is incredibly simple to think about. Think about a ball that's been lifted up in the air. If you remove your hand from the ball, if you're holding the ball up, you remove your hand, what's going to happen? Very clearly, the ball is going to fall down, and after it bounces around a little bit, it's going to settle on the floor. Think about energy. Think about potential energy. What's true about the potential energy? Well, we know that the potential energy is at the lowest it could possibly be right here on the ground. The ball was seeking the lowest possible potential energy arrangement of the system. Well, guess what? Atoms tend to do that as well. Just a little bit more complicated. With atoms, though, we're not talking about balls falling to the ground. We're talking about systems of electrons and protons and things. So here's the general rule of thumb. Atoms tend to have the lowest possible amount of potential energy that they can when they have 8 valence electrons. We refer to this as the octet rule, that word octet referring to 8. Now, there are some exceptions. Hydrogen is an exception because he's stable and, so to speak, happy. He's reached the lowest potential energy minimum with 0 or 2 electrons. Helium is stable with 2. Lithium is stable with 2. Beryllium is stable with 2 or 4. Boron is stable with typically 4 or 6. So those are our only exceptions. I'm not going to make you know them. But listen to what I'm saying. Atoms will seek to change their number of outermost valence electrons until they have achieved 8, an octet. So in order to achieve an octet, an atom will give up, will lose, or will receive, will gain electrons in order to achieve that octet. And in doing so, the atom has become what we refer to as an ion. An ion is an atom that has gained or lost electrons and thus developed an electric charge. Let me give you an example. Fluorine. Fluorine has an atomic number of 9. So the Z for fluorine equals 9. What does that tell you? That tells you that it has 9 protons and 9 electrons, right? Let me do an energy level diagram for fluorine. Fluorine is in group 17 in the second period. This tells me that it has 7 valence electrons in the second energy level. So I know it has 2 electrons in the first energy level. This is the nucleus. And I know that it has 1, 2, 3, 4, 5, 6, 7 valence electrons. 7 electrons in the second energy level. If I look at the periodic table, it is in the second period. It's 7 over. It's in group 17. So it has 7 valence electrons. Well, it's really close to having an octet, isn't it? It just needs to gain 1 more. So let's imagine that it gains an electron. It's capable of picking up an electron, and it gains that electron. So it no longer has 9 electrons, and it has 10 electrons. So think about this. Do the number of protons and electrons balance each other out now? No. It now has more negatively charged particles. It has gained an electron. Therefore, it has more electrons than protons. Therefore, we can say that fluorine has become an anion. This is an ion that has gained electrons and thus has a negative charge. Fluorine has a negative charge. Now I would write that like this. I would write an F with a minus sign in the upper right. This means that fluorine has gained 1 electron. There's an invisible 1 right there that we do not write. In chemistry, whenever there's a 1, it is implied. So fluorine has a negative charge. This would represent a fluorine 1 minus ion. Why? Because it wants to be stable, it wants to reach the lowest possible potential energy arrangement. To do that, it wants an octet, so it has gained an electron. Let's think about sodium right here in group 1, period 3. Its atomic number is 11. 8 electrons in the second energy level, and only one valence electron in the third energy level, just like I thought, because it's in group 1, period 3. One valence electron in the third energy level. What is a valence electron again? The electrons in the outermost energy level. So, sodium is not stable. He's not happy. He's not at his potential energy minimum. He's not living his best life because he does not have an octet. How can sodium get an octet? Well, I guess we can think about it like this. There are two ways. Sodium could gain 7 electrons, or is there another way for it to have 8 electrons in its outermost energy level? What if it just lost this electron? What if this singular lonely electron went flying off somewhere else? Therefore, this third energy level is no longer being utilized. It goes away. What is left over? Yes, right underneath that third energy level, we have the full octet in the second energy level. What does sodium now have because it lost that outermost valence electron? Remember, it had one more electron out here in the third energy level. If it loses it, what does it have right underneath? It has a full second energy level. It has a full octet. So that represents the stable minimum potential energy that sodium can achieve. So sodium, this ion, would no longer have 11 electrons, but would have a total of 10 electrons. So what kind of ion is that? It now has more protons than electrons because in order to become stable, happy, live its best life, reach the potential energy minimum, it has lost an electron. It's gone from 11 to 10 and now has more protons. What kind of charge will that have? More positively charged things. So it is a sodium 1 plus ion. Remember, we never write the 1. So a sodium 1 plus ion, we refer to those types of ions as cations. These are ions that have lost electrons and thus developed a positive charge. We've already done sodium here, so I know that's Na plus. Let's start up here at the top. What type of ion will chlorine form? Chlorine is, let's figure out where chlorine is on the periodic table. Chlorine is right here. In fact, all of these are in period 3. And I'm starting over here with chlorine. How come I'm not worried about argon? Well, how many valence electrons does argon have? It's in group 18. Argon already has 8. So it is already stable and happy. In fact, all the noble gases, except for helium, helium has 2, all the noble gases already have 8 valence electrons. They already have their octet. They're already stable. It turns out, as we'll see later, that the noble gases, they don't like to undergo chemical reactions to form chemical compounds because they're already happy and stable. They don't need to shuffle around their electrons. Chlorine, though, does. Chlorine has how many valence electrons? Chlorine has 7 valence electrons. So I'm going to draw an energy level diagram for chlorine. This is the last time I'm going to do this. And then I'll make it simpler for you. So chlorine has 17. That's the atomic number. And I know that it's in the third period. So that tells me it has 17 protons, 17 electrons. The protons are found where? In the nucleus. What else is in the nucleus? The neutrons. I'm not worried about those, so I'm going to represent that with a dot. And how many energy levels do I need to give chlorine? 3, right? Because it's in the third period. So 1, 2, 3. There we go. So, what is chlorine going to do? Well, it's so close to having an octet. It's so close to being like that noble gas argon that I think it's very clear that it just needs to gain an extra electron. So if chlorine can somehow snatch up an electron from its environment, gain that extra electron, now it's stable, now it's happy, now it has reached a potential energy minimum. So what type of ion has it formed? It's gone from 17 electrons to 18 electrons. It has one more electron, so that's a chlorine 1 minus. It is negatively charged. Sulfur is right here on the periodic table. It has 6 valence electrons because it's in group 16. Chlorine had 7. What did chlorine do again? It gained an electron to become like argon, right? It's only 1 away from having an octet like argon. So chlorine gained 1. Here's an incredibly easy way of doing this. Just look at your periodic table, put your finger on the element, and count over to the nearest noble gas. Chlorine was here, and it's one space over from that nearest noble gas, so it gained one electron to form a Cl- ion. Sulfur is right here. It's 2 away, so it's going to gain 2 electrons. Sulfur will gain 2 electrons to become stable, to have an octet, to become like argon. What do you think I'm going to write for sulfur? It gains 2 electrons. Sulfur 2 minus, that's correct. Let's think about phosphorus now. Phosphorus is right here in group 15. How many valence electrons does it have? Remember, you can find the last digit of the group number, and that will tell you the number of valence electrons. It has 5. Another way of thinking about it is that it is 1, 2, 3, 4, 5 over in its period. It has 5 valence electrons in the third period. So what can phosphorus do to become stable? It can gain, remember I find the nearest noble gas, that's argon, and I count over to it. Phosphorus is going to gain 1, 2, 3 valence electrons. So if phosphorus does that, it has gained 3 negatively charged particles, 3 electrons. It's going to develop a 3 minus charge. Now, am I telling you that phosphorus becomes argon in that way? No, it's still phosphorus. It still has 15 protons, but now it has 18 electrons. 1, 2, 3. It's gained 3 to become like argon. It now has 18 electrons, 15 protons. It has a 3 minus overall charge. This is a negatively charged ion. It's a 3 minus anion, and it's stable and happy. It has an octet. What about silicon right here? That was the next question. We're just going down period 3. Silicon. Well, this is tricky because silicon has 4 valence electrons. So is silicon going to gain 1, 2, 3, 4 to become like argon? What else could it do? Well, it could also lose 1, 2, 3, 4 and become like neon, couldn't it? It's right in the middle. It doesn't really have a closest noble gas. Is argon closer? 1, 2, 3, 4. Or is neon closer? 1, 2, 3, 4. Well, the secret is that things in group 14 typically don't form ions. It turns out that these two elements down here, tin and lead, they do. But these up here, they don't. So we're not going to worry about it. Remember, I'm only going to be asking you about the first 20 elements. So silicon, carbon, they don't form ions. Let's think then about aluminum. Aluminum would like to achieve an octet. Right now, aluminum has 3 valence electrons. So what's the simplest thing for it to do? Is it going to gain 1, 2, 3, 4, 5 to be like argon? What else could it do? It could lose those 3 that it has, because right underneath the 3 valence electrons that it has a full second energy level, just like neon. So argon will lose, so aluminum will lose electrons. It will lose 1, 2, and then it will lose 3 and become like neon. If aluminum loses 3 electrons, it now has 13 protons, 10 electrons. It has more positive particles. So it's going to have a 3 plus charge. It's a 3 plus cation. So here is the pattern. Group 14, they don't form ions. Anything to the left of group 14, they will form what we call cations, positively charged ions. What about the other side of group 14, group 15? Group 15 has 5 valence electrons. It would like to have 8. So group 15 is going to go ahead and fill up its outer energy level. Instead of aluminum, magnesium, and sodium, instead of groups 1, 2, and 3, which are stripping away their outermost electrons to reveal the full energy level beneath, these are going to go ahead and fill up their energy level. Phosphorus will gain 3 to become like argon, 3 minus. That's an anion, a negatively charged ion. Sulfur will gain 2, 1, 2. Anything in group 15 will gain 3. Anything in group 16 will gain 2. Anything in group 17 will gain 1 to develop a 1 minus anion. So these are the patterns you guys need to know.